Hello, my name is Michael McCulloch, and today I will be presenting to you on the topic of Stable Diffusion and ComfyUI. We'll go over a brief introduction, some motivation for using the tool, and then we'll talk about the core architecture, some of the technical components. We'll talk a little bit about samplers and schedulers, and I'll show you some practical implementation through ComfyUI. The first question you might have is, why do I care about Stable Diffusion? I have done my best to produce a sketch of the typical Stable Diffusion user. They have lots of money, perhaps little artistic talent, and they wish to make an exchange. I'm sure everyone has heard a bit about Stable Diffusion and some of the models that exist in that space. Stability AI spent all of their investors' money on Stable Diffusion 1, 2, 1.5, 2, and Stable Diffusion XL before realizing that it was their function to generate profit. So they finally delivered Stable Diffusion 3 and 3.5. Black Forest Labs delivered Flux, which is comparable in quality to Stable Diffusion 3.5. However, the court of public opinion has determined Stable Diffusion 3.5 is just a bit better. As far as the core architecture, we'll cover clip, VAE, and two different approaches to producing images from noise or from feature maps directly. We'll talk about why we have to go the route that we take, and then we'll get into some examples. So this is my depiction of a simple noise to image pipeline. Just because it's a bit blurry, I'll talk through it a bit. You start with your noisy image on the far left. It's 512 by 512 or some other square. You encode it through the VAE, which does a little bit of magic. You get a latent space. You put it through your diffusion model. Itself is guided by additional magic provided by clip. Once that diffusion model has done its task, you are presented with a less noisy image represented in latent space. You can decode that with your VAE, and you yield a new, slightly less noisy output image. If you do this 20 times, you can generate a fresh image from pure static. What is clip? Clip is the solution to the problem, how do we describe images in terms of words? And the process for generating a clip model is pretty straightforward. It's actually two models that are trained side by side. You have a clip model, the image encoder. You have a text model, the text encoder, or unclip, as it's sometimes called. And you're going to train your image model such that it converges. And what you will have is a new model that takes images and produces an embedding output that represents that image in embedding space. Nothing super fancy. We then treat that as the source of truth for our text embedding training process. So we take text descriptions of those images, we embed those through our text embedder, and we train against the embeddings produced by the image embedder for the images that had produced those descriptions. And we get something a bit like this. I've provided it an image of Shrek and an image of Captain Riker, and I've told it I would like you to additively combine these embeddings. And this is exactly what we get. We get a picture of Shrek in some combination of ogre Starfleet uniform. He's holding an onion. He's got a comm badge and everything. It's a mess, but it is a coherent image because the clip understands what you mean. Variational Autoencoder is the piece of the puzzle that makes it all possible, but it is possibly the least interesting piece. It serves to take the noise to image problem and turn it into a latent space to latent space problem. The latent space is orders of magnitude smaller. You'll often have a 1K by 1K image, and that's represented in 128 by 128, a matrix of 128 by 128. You can process noise on that much more efficiently on consumer hardware than a full graphics card, which was the approach before Stable Diffusion really became ubiquitous. This is a more detailed overview of Stable Diffusion. There's not a lot extra going on here. The interesting part is the UNet, which is a fancy way to solve the problem of keeping around information for later, so that when we do the inference pass, we can refer to stuff that we've already generated in prior runs. Stable Diffusion 3.5 differs significantly from Stable Diffusion XL. For Stable Diffusion XL and prior models, they stuck to a UNet that they just made it bigger. A UNet is a way of converging information. Like I said, on the way down, you want to keep some information so that on the way back up, you can retrieve it. Transformer, the transformer used in Stable Diffusion 3.5 is the same kind of transformer that you would see in a language model, but it just has a different heritage. Other than that, the layout of the model is largely the same. The interesting thing that we do here is that if you notice in SDXL, when we take the tokens, we embed the text to token space and use that as a guide. What we're doing here is we're taking the text, we're embedding it, and that is put into token space. It's not the guide, it's the prompt. We don't tokenize. The easiest way I can explain it is it's similar to the deep talk that we did a few weeks ago, where representations of DNA or chemicals would be represented as embeddings directly in the token stream. So given a UNet, this is the user story for a person, for the UNet itself. Given an image, I want to predict what noise exists in this image so that I can remove this image, the noise from this image later using a scheduler. And as a scheduler, I want to calculate how much of that noise that the model has predicted that I'm going to want to remove from the image. And the reason we can't just predict the image directly is because it's really, really hard to do that. We could if we had enough compute, but it's easier to predict noise. Pictures of noise don't have opinions about apples or trees or people. So there's less need to actually worry about the content of the image itself if you do a noise-based approach. You still need to train the model end-to-end on descriptions of images and full images, but the model itself learns noise to noise, which is considerably easier. So you get more variation, you can generalize it, you can train something in under a human lifetime. A noise schedule approaches this problem of scale from a different angle, so we use both. We could train an image that was noise to image, but using intermediate steps where it's noise to clean, noise to clean, noise to clean, makes each step easier to solve for. The difference between something like diffusion, where we want to remove noise, and something like modulation, is that with modulation, we want to generate the image directly from the feature maps. We're not really concerned with noise directly, and we're not directly looking at the image. We're handling the embedding representation of our clip output and our image content directly. There's no noise, it's just a transition from an empty page to a full image. The description of the construction of feature maps is one of those things that can really only be explained mathematically. And this equation that I've got bolded on the screen just says that the new feature map is produced by taking the embedding space, scaling your old feature map by that through element-wise multiplication, and then shifting it over a bit. So the idea is if we have a feature map and some of the features are close to what we want to scale those up. If some of the features are far away from what we want, we scale those down. And then we can shift the whole thing. That's the purpose of modulation. Unpatching just means, if we go back to this clip here, we take our image and we produce noised patches. At the end of the process, we have a bunch of patches and we need to reassemble them. So we call that unpatching. This is the main process difference between the transformer-based approach and the UNet approach. With the transformer, it's very much like a language model. We're using self-attention, whereas with the UNet, we're using cross-attention. We deal with the embedding space directly, whereas with the UNet, we have to kind of lie to the network and say, hey, you're just generating noise, don't worry about the image. To sum up, the main difference that denoising, you're cleaning up a noisy image. Modulation, you're drawing on a blank canvas. That's the main difference. With denoising, the image generation is a side effect, and with modulation, the image generation is the principal action of the network. So, samplers and schedulers, there is a lot of variation in samplers and in schedulers, and they often work together, but you can mix and match them. The relationship is pretty straightforward. A scheduler determines the intervals. The model predicts the noise to remove, and the sampler uses the interval and the noise prediction to actually remove the noise. You just repeat this 20 times, or if you have the turbo model, 4 times, until you have a final image. I listed some of the samplers here. There are much, much more. This is not an exhaustive list. The main ones that you're going to be interested in when you're using Stable Diffusion is Euler. It's pretty basic. It's old school differential equation solvers. The ancestral samplers add noise before they remove it so they don't converge. Other than that, I would say that a discussion of all of these samplers is out of scope, but there are some that just work really, really well and some that don't. And that will depend more on the model that you're using than on anything else. Let's talk a bit about ComfyUI. ComfyUI is a node-based workflow. And the idea is, okay, we've got all these pieces of a Stable Diffusion model, the clip, VAE, the diffusion model, prompts, and we'd like to assemble it. And we could write Python, but maybe we want a more visual workflow and we want something more flexible, something we can share by embedding it into an image. That's really the problem that ComfyUI aims to solve, and maybe some of you have worked with workflow tools before. This is very similar. It's a node-based GUI for operating diffusion models. It exposes every seam between pieces of the pipeline as a node or a link between the node. Manages memory, and generally makes it possible to run pretty much all of these Stable Diffusion models on pretty basic consumer hardware. What is a custom node? It's very straightforward. It's got an input and it's got an output, and it does some processing. The processing can be anything you can describe in Python. The inputs and outputs have to be constrained to whatever ComfyUI inherently understands. And as we'll see, there are a lot of primitive types in Comfy. This is a full example of a custom node. Do not worry about reading the whole thing. The main points I want to convey are that, yes, there is a mapping, one-to-one mapping from structures in the class definition to the node that is rendered on the screen. because the class definition is interpreted and registered, and from that, the node definition is generated. Scheduler sampler pairs. This just tells it which function to call, where to put it in the UI, and whether or not the output is a collection. Tells it what inputs to use, and here we've defined the input types as the result of a function. Model, int, and float are primitive types, and those are their defaults. The return types, same story, we've just defined them as variables. Sigmas are the difference between sigmas, samplers, and strings are also primitive types. Sigmas is there as the computed result of our sampler for all of the different samplers that we might wish to use. Generate pairs. In this example, this code was used to generate all possible combinations of samplers and schedulers. So we accept a list of models that are compatible and how many steps we want to use, and we return the entire list. Finally, we register it directly with the ComfyUI runtime. And that's what we get. I did have a demo here of it running in real time. And I will just put that here while I say thank you for watching my presentation.